degree 6. Then you may have at most 5 turning points, but there's no guarantee that you can always have 5 turning points. Some polynomial of degree 6 may have 5, some other may have 3, some other may have just 1 turning point. Okay? And polynomial of degree 3, you may have 2 turning points or no turning points. Okay? Look at polynomial of degree 3, easy to draw this way. 2 turning points. This is one, this is another. Or you may have a polynomial of degree 3 this way. No turning point. Graph keep going up forever. What about polynomial of degree 1? It's a line. No turning point. Okay? The line go up forever. The line go down forever. Okay? What about polynomial of degree 2? Quadratic function. Remember, polynomial of degree 2. It has exactly 1 turning point. So you see either a parabola this way or parabola this way. So go down, go up, or go up and go down. That's it. That's about turning points. Okay. I think that's how much the book gave you in this section, but let me extend a little bit more. All right. So that's the advantage of the lecture. And by the way, when I give you a lecture in class, I try to give you, pick up the most important things that put on the clip for you guys to watch. But I strongly encourage you guys to read the book by yourself. Okay, you learn more from it. If you have any questions, please feel free to ask. The book gives you a lot of information as well. I'm not covering every single word in the book. Just try to bring you the main points that you guys need to learn. Okay, but not everything. Okay. Let me try to extend the concept a little bit more. What are those degree, leading coefficients, and turning point? Well, tell you, what will you get from it when you learn those things? Okay. First of all, let's talk about even degree polynomial. So you have two types of functions when you have even degree polynomial. This way or this way, right? When you have even degree. Even. N is even. And the both ending behavior of the graph will be in the same direction. So you see what? Either at first it starts going down and at the end it's going up, or at first it's going up and at the end it's going down. And I claim that those even degree function will always, even degree polynomial function to be clear, will always give you a maximum or minimum. You see why? They go down at first, go up at the end. Eventually you got to hit the bottom. Same thing here. Go up at first and go down at the end. Eventually at some point, you're going to hit the top, right? So for sure, those graphs are going to give you a maximum or a minimum. Of course, the simpler case is parabola. Okay? So you know that those functions are going to give you the extremum, the max or mean. What about the odd degree? You're going to see what? Positive leading coefficient, the graph tends to go up. Negative leading coefficient, the graph tends to go down. So for sure, for odd degree polynomial, and it's odd. And what? One plane is going up, the other one going to go up as well. One plane is going down, the other one going to go down as well. And what do we get from here? It guarantees you that the graph will always intersect the x-axis. Always. Because what? Eventually the graph is going to get all stressed out all the way from negative infinity to positive infinity for the y value. Okay? So we guarantee you that. So you guys are going to have the x-axis. I'm sorry, the x-intercept. Maybe one, maybe a lot. Who knows? But for sure you have one. At least one. And what do we learn in here? If the function has an intercept, for sure it's at a 0. For sure it can be factored out with a linear factor. Okay? We good? So I will tell you what, if the polynomial function has an odd degree, then it's going to have a solution. It's going to have a root or it's going to have a 0. Guarantee. Okay. Next question. How do we find the zeros if we know that it has one? Okay. Let me introduce you another item for the day. Item number 3, big 3. It's a very famous theorem, very popular theorem. It's going to help you, well, if not be able to find the exact zero of a polynomial, at least it's going to help you to approximate a zero of a polynomial. And the theorem name is intermediate value theorem. Okay. Because there's a lot of versions of intermediate value theorem, and I believe in intermediate algebra. I'm sorry, in pre-calculus algebra, we're gonna show you a very simple version of it. Okay, and it's help you to understand better if you see something simple. So first of all, let me explain the idea of the theorem, and then after this, I will write it down for you formally. Okay, I think I need more room, so let me bring it up. It's number 3. Intermediate value theorem. Okay, it's abbreviated by IVT, intermediate value theorem. Okay, so what is the theorem is about? What is it talking about? Say if you have a function f of x, and we have some condition with this function. Function f of x is going to be continuous on an interval, a closed interval from a to b. Means what? When x varies from a to b, you're going to graph the function with one curve. Okay? One curve when x varies from a to b. Right? No gap, no holes between a and b. Okay. And moreover, more than that, say a is from here, b is from here. Okay? It's a. I don't need to write that way. Just a. And b. If you plug a into the function, you see why I use square bracket right here, because it allows that a is on the domain. So if I plug a in the function, I have a point that is, say, below the x-axis. This is f of a. If f of a is below the x-axis, means what? F of a is a negative number, right? It's below the x-axis, the y value. And if f of b is above the x-axis, f of b is up here. You plug b in for x, you got the y values for f of b, so above the x-axis. So the first endpoint is below the x-axis. The second endpoint is above the x-axis. Okay, one below and the other is above. And since the function is continuous, it means when you graph the function when x runs from a to b, you have to connect the first point to the second point. You know what the theorem say? The theorem say that for sure that curve will intersect the line segment AB somewhere. Another word, for sure that you have the x-intercept, let's call it C. Another word, for sure that this function will have a 0. It means f of c is equal to 0. Another word, for sure that f of c has a linear factor of c minus 0. That's what we learned before. Okay? So even though we still don't know what value of c is, but I know for sure that c is going to be somewhere between a and b. You guys see why c cannot be outside? Say if you connect the lower point from the upper point, you connect this way. And you can learn the c could be right here. You guys see what's wrong with that? This curve, the red curve, will fail the vertical line test, and it's not going to be the graph of the function. Okay, so for sure c is going to be somewhere between a and b. So you guys see the idea of the intermediate value theorem. You have a continuous function of the interval, and fa is positive, fb is negative, fb is positive. One point is below, one point is above. There will be a zeros or a solution or a root somewhere between a and b. Okay, and of course the other way around going to work as well. If fa is positive above the x-axis and fb is negative below the x-axis, you still have the same result. All right, now that you got the idea of the theorem, let me just write it down formally. If given, about this, let f of x be a continuous function on a closed interval AB. Now, we have to talk about the condition right here. One point is below, one point is above. Now I'm going to write this way. If f of a times f of b is negative. Now let me explain to you what I mean by this. You guys see the two factors right here. F of A is a number, F of B is another number. You multiply the two numbers together, you got something negative. Two cases. Either a negative number times a positive number means what? Negative means below, positive means above, right? Or the other way around, positive times a negative number. So what? Well, above times below. So either way, you have one point above the x-axis, the other point is below the x-axis. So with this writing in mathematics, you see the beauty of it. It includes all the cases that we want to talk about. If that happened, then there exists a number C. And more than that, that C is going to be somewhere between A and B. C is going to be between A and B, such that f of C is equal to 0. And by saying f of C equal to 0, we say that C is the 0 polynomial, or C minus 0, x minus C. I wrote it wrong here. X minus C. I'm sorry. X minus C will be the linear factor. Okay. Correct that for me. Say it's supposed to be x minus C. Okay, and that was the theorem. Now, let me show you guys the use of this theorem. This is just one of the use of the theorem to approximate the solution of a polynomial. Okay, and before we start, I have to claim that this method of approximating the zero is not the best way, not at all, but it works. Okay, and the books show you this, so I'm showing you guys as well. And I claim that later on, you may find much better methods to find the approximation of a solution way faster than what we are about to see for now. So I have a polynomial example. F of x equal to x cubed plus x minus 3. Okay? So we see what in here. This is a polynomial of degree 3 with leading coefficient 1. So positive leading coefficient and degree 3 odd degree, the graph tends to go up. So for sure, this one going to have a 0. Okay? Question is, can you approximately find a 0 for that polynomial? And I claim that I can use intermediate value theorem to find a 0. Okay. Let's try x equal to 1. What do I have? F of 1 is equal to 1 cubed plus 1 minus 3. So 1 plus 1 is 2. 2 minus 3 is negative 1. And this is a negative number. Okay. Let's try x equal to 2. I'll just try random number. Actually, it's not random because I chose an easy example, so I see it. Same method worked for other function as well. Okay. X equal to 2. So you got what? F of 2 is 2 cubed plus 2 minus 3, which is a plus 2 minus 3 equal to 7. It's a positive number. Okay? So, graphically, what are we seeing in here? When x equal to 1, you get negative 1 right here. Okay? We got negative 1 right here. X equal to 1. F of 1 is negative 1. X equal to 2. F of 2 is 7, so we're up here. So, we have one point below the x-axis. We have the second point above the x-axis. Okay? And of course, all polynomial functions are continuous all over the domain. Okay? So, according to the intermediate value theorem, to connect the 2 points, for sure it's going to intersect the x-axis at some point, C, in between 1 and 2. And by the way, I'm just saying it's going to intersect at some point. I did not say that it's going to be a unique point. Okay, it could be multiple points between 1 and 2. The graph may be like this, who knows? You guys see? So at least one value, one intersection between 1 and 2. So I know that C is somewhere between 1 and 2 by the intermediate value theorem. Even though I still don't know the exact value of C, but at least I know that C is going to be equal to 1 point something. 1 point something. Okay? Because it's between 1 and 2. Now, what can we do? to increase the accuracy of C. Okay, find more C more precisely. And here comes the book method. Of course, it's using the intermediate value theorem, and this is how the book is going to take care of the problem. It's going to make a table. Show you a table. All right, you plot the value of x, and this is the function f of x, and you try all the value of x somewhere from 1, 1.1, 1.2, 1.3, 1.4, all the way to 1.9 and 2. Okay, let's try to plug the numbers in. Say I plug in x equal to 1. I receive a negative value. I plug in x equal to 1.1. I receive a negative value. Let me try to plug it into a calculator. Let me find a calculator, okay? Let's see what we have. All right. And then I see what x1.2 is a negative, and then 1.3 positive. I just try to plug the numbers in and grab my calculator. This is what I see. Okay, and then positive, positive. Okay, you may check my work, it may be wrong. I just grabbed it quickly, so I'm not sure. Okay, so what? You plug in 1, you got a negative value come out. Plug in 1.1, you got a negative value come out. Plug in 1.2, you may have a negative come out. 1.3, you get a positive number come out. Just make it that way. And you're going to use the in-value theorem again. Say what? The value of C is going to be somewhere between 1.2 to 1.3. All right? So it's not just 1 point something. It's going to be, C is going to be 1.2 something. And now, you want to know what something in here, you try some value between 1.2, 1.21, 1.22, all the way to 1.3, and you have one more decimal. Of course, it's long, take a lot of work, but at least it works. It gives you the approximation of the solution. Okay, and that was one of the use of the intermediate value theorem. Okay, and actually this is the end of section 2.2. Thank you very much for watching, guys. If you have any question, please don't hesitate to shoot me an email. All right, I'm more than happy to help you out. Thank you and have a good day. Bye-bye.